All right, here we go. All right, so I did have a demo for this presentation, but it's not relevant anymore. But I will talk about what it is. So what's really cool about RISC-V is that it's a fairly new architecture. For those that don't know, and I'll cover this more in a bit, but RISC-V was only invented maybe like 10-ish years ago, but it didn't really get popular until recently, like in the past couple of years. I've been participating in RISC-V since about 2016, I want to say. And at the time, we had our first ever CPUs that were starting to be released. Sci-Fi created the first ever silicon. And they produced a little Arduino type microcontroller board called the Hi-Fi 1. And it was really exciting because you could actually play with a physical chip. But it did use the initial architecture version of the RISC-V ISA. And so this demo was actually a hack that I put together in attacking that initial architecture. So what ended up happening was they had a logic flaw in the instruction set architecture where you could manipulate the page tables based on the privilege model that they define. And you could bypass the security model of the implementation and go from the kernel layer to the BIOS layer, essentially. It's like the equivalent of that in RISC-V terms. So the demo was actually showing that model. It's not that exciting when you're looking at text scrolling by on a screen, so we're just going to skip that. Plus, it's actually not relevant anymore because we fixed that architecture flaw thanks to that exploit that I wrote. So that's kind of passe, but it's important to note because part of the thing we're going to be talking about today is not just developing zero-day, as in like developing shellcode, writing usual architecture, specific exploit ROP chains, things of that nature. We're going to talk about the architecture itself that you have to be aware of when you're developing those exploit tools. And that's really relevant in RISC-V because even though it's another RISC like ARM or MIPS or whatever, Spark, the subtleties are really important to understand. And also the architectural challenges are important to understand so that once you actually develop your workflow, you can do so at the privilege layer as well as the application layer and be more effective at attacking both applications and kernel layer abstractions. So a brief, Sam will give me an excellent intro and I appreciate that. He's a great friend, so he's always going to be, very kind to me, but I'll give you guys a little bit of a background for those that don't know me. Because I've been in information security and doing cybersecurity zero-day development for almost 20 years professionally. I started doing professional work in 2003. And I've always focused on two things, embedded systems and zero-day. So I have focused on the embedded ecosystem, which was initially, distributed systems. When we called it machine to machine, we called it telematics, and then it evolved into IoT. I was really blessed and lucky to be one of the first researchers in this space, along with, the great Barnaby Jack, who sadly we lost, right? But, there were only a couple of us at the beginning of IoT hacking in general. And I was lucky enough to be one of those people just because embedded systems always interested me. And I envisioned a future where we had, log4j vulnerabilities on toasters, which is sadly our modern reality, right? But, even back 20 years ago, you could see it coming, right? Because everybody wanted to build new technology with computer chips involved. And I said to myself, like, well, this is going to be a thing, right? Like, I have to be a part of it because that's a really exciting world. The future is going to be a world where we can interact and control anything from anywhere. And that's just exciting, right? So I was the first person to hack a car, first person to hack the global cellular system with Nick DiPetrillo in 2009, which was his idea, but I was lucky enough to be a part of it and help accelerate that to the forefront of computer security at the time. And we did some things that really changed the world. We shaped the way that telecommunication occurred, especially in the United States. We had some walls brought up in our SS7 system in the United States as a result of the work that Nick and I did. And that was really relevant to the embedded system space because the overlap between cellular systems and embedded systems was not clear at the time. But once we really dove into that hack, it made a lot of sense, especially when I did the first ever AGPS hack, which was attacking a tracking device that was also rebranded and used for things like tracking criminals in their homes. So one example of that you guys may get a kick out of is when I did this hack, it was actually, posed as a device that people would use to track their kids by throwing this little device, this tracking device in kids' backpacks. So they're, walking to and from school, and parents can make sure their kids are actually at home or where they say they're going to be. The same computer program, essentially, and the same PCB was rebranded and used for ankle bracelets for tracking offenders that were doing in-house jail time, essentially. So people that were forced to stay home and had a tracking bracelet on. So felons, things of that nature that weren't actually housed in a prison. And at the time I was working for ISAC Partners, the notorious, if not infamous, information security consulting group that got acquired quite a few years ago. But at the time, this was a brand new area of research. And we were actually getting contacted by the Mexican cartels. Guys in prison saw what I had done, and they realized that their tracking bracelets had the exact same circuit boards in it. And they tried to reach out to ISAC Partners and reach me through ISAC Partners to connect them with their lawyers, or connect us with their lawyers, and then prove that their tracking bracelets were being hacked. And they were put back in prison because they didn't actually leave their house. The FBI secretly was hacking their tracking bracelets and making it look like they weren't home when they really were, which is just crazy, right? So that kind of gives you an idea of, at the time, back in 2009, 2010, we really started to get a big picture of how much embedded systems and cellular technology overlapped for the future of what IoT was going to be, what that was really going to mean for society, and the challenges that we really face in, bringing this new world to fruition, right? So it's not just the first car hack. The first car hack was, it was really fun and a huge privilege to be able to do that. But at the same time, almost the tracking device gave us a better peek into the substantial challenges that we would have, because the car hack is almost obvious, right? Like, you don't want anybody to drive you off the road. But hacking a tracking device that's meant for parents to monitor their children, how does that somehow affect the Mexican cartel being able to argue that they're being hacked by the FBI? Like, that's just bizarre, right? So that's my history. My history in IoT and embedded systems is just weird. But that kind of comes with the territory, right? Like, being a hacker, being lucky enough to be one of the first in this space, it's been very strange. So when I got interested in RISC-V, it became really clear that RISC-V was going to be the next big thing in computer architectures, and kind of like how cellular had a really large influence on IoT's design and functionality and the challenges. RISC-V's architecture is going to be the exact same from the CPU perspective. So currently today, I'm actually, I consult on the side, but I also am running a security practice along with my very distinguished peers, Matthew Fulton, who's probably the best, and my apologies to everybody on this call, but the guy's one of my closest friends, but in my opinion, he is probably one of the best, if not the best, application-centric hackers that I know. And so I'm working with him and James Braley, who is a infrastructure security specialist, and we are running the security program at Geotab, which is really exciting. And obviously, I work for RISC-V on the side. I'm the chair of their security response team. It is a unpaid thing. We're a nonprofit, so I should use the term work for very carefully. But we are putting out a bunch of material to allow people to work with RISC-V. So if you find a vulnerability with RISC-V, we will actually work with you to identify how to integrate that into RISC-V's model. But the exciting thing about that is we're trying to figure out how we can actually promote our researchers, right? So that's actually extremely important because, you know, usually when you do a bug crowd style engagement, right? You get somebody on HackerOne, they find a cool thing and they rock up and show their, you know, demo, and they get a little kudos, maybe in an email list or something like that. But we really want to demonstrate that RISC-V is security first from an architectural perspective. So what I hope to do is figure out a way that people that find significant vulnerabilities in our ISA can actually get their name in the ISA spec. So like when you use, you know, your CVE list when you're going to get a job and people say like, oh, what have you done? And you present your CVE list, you can actually just point people at the RISC-V specification, like the architecture ISA spec, and show your name in that list as one of the contributors to that spec, which would just be badass, right? And that's really important because when people find those things at the ISA level, it affects every single person that develops a physical chip. Those concepts get introduced to the physical security layer of every chip produced from that ISA. So in my opinion, if you find a significant vulnerability, you absolutely deserve to get your name showcased as being a contributor to that product. So I'm hoping we can change the game a little bit and influence at the CPU level those kinds of changes. It's very exciting. So we'll kind of dive in here to the actual RISC-V privilege model and talk about why it's different, right? Because everybody knows the standard ARM model, the standard x86 model, like these are all pretty well known. And RISC-V is similar, but there are some important alternatives, I would say, to this. It's a really interesting mix and match model. So you've got your usual 4 layers, right? Everybody's familiar with userland where your applications sit. Most people are familiar with some kind of a supervisor layer, no matter what you call it, right? The ring at which the Linux kernel sits, or FreeRTOS, or whatever you have, what your kernel is. That is the supervisor layer. That's what our terminology is. We deprecated the hypervisor layer, which would be under the supervisor layer, because essentially the hypervisor layer would control however many supervisors you have, right? So if you wanted to run Linux in concurrency with FreeRTOS or just multiple Linux instantiations, you would do that at the hypervisor layer level. Then we kind of deprecated it and said, maybe we're not going to do this. And that was, I think, back in 2017 that we had made that decision, but actually we're bringing it back now. So no longer deprecated. We're going to, you know, figure out how to implement the hypervisor layer again. So I believe that spec is still in development. We may have a release on that shortly, if not at Summit in the past week, which I was not able to attend to, sadly, because of a COVID quarantine, but whatever. It's that's just what's happening now. Stupid COVID. And then obviously, you know, like every architecture, you have essentially the, you know, BIOS layer, or, you know, the metal layer, if you will. We call that machine layer. That's your highest layer of privilege. That is higher than the kernel itself. So where we usually think the kernel is having the highest layer of privilege in a architecture, and in most cases, even if that's not true in like ARM or x86, it is true in function, right? And what I mean by that is the kernel really has control over all of the devices and the device configurations on most x86 and ARM implementations, right? So even if there is a BIOS, like usually the Linux kernel or whatever kernel there is can tune that machine layer, privilege layer as it pleases. That is actually not the case in RISC-V. It is possible to configure the CPU that way, it is possible for the firmware that runs at first boot, cold boot, to configure the system that way, but that is not the default. And that's actually what's really exciting about RISC-V is you have that choice. When you configure your CPU, and not just from a I'm building a silicon layer perspective, but from a, I'm going to boot a secure machine layer ROM, if you will, and then transition that to a, bootloader that then loads and executes a supervisor layer Linux kernel. Either configuration can actually tune the environment so that machine layer is secured from supervisor layer, which is really, really cool. And I'll talk about why more deeply in a minute, but the obvious attack model is obvious attack model is obvious, right? We want to transition from user to supervisor. If you are attacking an application, you just want to hit user land and get a shell in user land. But if you're thinking about it architecturally, you obviously want to transition into kernel land where possible, because you're going to have the most control there. If you want to attack an embedded system, your goal is always the machine layer. And the reason for that is the machine layer is where all the security keys will be. And they will not be guarded from you if you have access to the machine layer. So you can think about that. If you're thinking about it from an ARM perspective, think about the analog of secure world in ARM that is very similar to, but not exactly the same as, machine layer in RISC-V. We'll talk about that in a bit, but kind of in secure world mode. Stupid thing. That's the spam call I'm talking about. All right, so.
Hey, sorry, Don, sorry to interrupt, but there's a question in the Q&A.
Yeah. Let me dive into that. Can I know which distro 0-day are we building now, whether it's a Windows or Linux based? Hey, great question. So RISC-V being a CPU architecture can really run anything, right? So Windows could in the future be ported to RISC-V. But currently, being kind of a new architecture, it's focusing on Linux, BSD, and real-time operating systems. So Windows itself is not really in our ecosystem yet. It would be really exciting if in the future we did see Windows on that. But I would really look at RISC-V from the perspective of a similar ecosystem to ARM. Like, you're not really going to see Windows on it. You may see Mac on it in the future. In fact, one exciting thing about RISC-V is that we already have large corporations, building RISC-V processors, and that may or may not include Apple. I've heard rumors about that, but actually I'm not quite sure if that's true or not, but I have heard good rumors. But we also have, Google and Alibaba and some other major companies are building RISC-V silicon now as well. So we will be seeing it quite soon in things other than embedded systems, which is really exciting. So yeah, I would think less from a Windows perspective and more from a Linux perspective for now, if that makes sense. Cool. So to dive back to the attack model, in an embedded model, our goal is always machine layer. In a normal server model or a desktop model, if you are thinking about it from that Windows perspective, you're going to be focusing more on either the app architecture or the kernel. But generally, in RISC-V, in an embedded systems model, you want to expose all the security keys. And really for desktops, that's going to be true soon anyway, as well. And the reason why I say that is a couple of guys gave me some crap for this a couple of years ago, but I predicted that Mac was actually going to be deprecated in favor of iOS-based devices. And people thought, that's crazy. People are always going to want desktops and laptops. Why would you say that? You know? And the reason why is actually engineering based. So it was my conjecture at the time that Apple was kind of looking at their ecosystem and saying, wow, we really have a split architecture here. We've got Mac OS X, which is one ecosystem, but then we've got iOS, which is a completely different style of ecosystem. And we're building all this iOS-based technology. And people aren't really buying our desktops and laptops anymore like they used to. They're mostly focused on embedded systems. And the amount of application diversity that we have on the desktop and laptop is shrinking, right? People are using the same apps over and over. And now those apps are more and more available on iOS architectures. So instead of having all of this money split in two different engineering buckets or ecosystems, if you will, it's almost easier to consolidate everything into one platform. And the obvious platform is iOS, because iOS can move from device type to device type. And so now we're kind of seeing that on the Mac side, right? They're migrating to ARMs. They're reducing Mac OS X capabilities to be more iOS centric. Those APIs are becoming more iOS alike, and the integration is becoming stronger. So I think that we're going to see desktops and laptops deprecated. And the important point about that, right, is if you're thinking about it from a Windows perspective, from a desktop, laptop perspective, even desktops and laptops will have security keys. I mean, they already do right now, but those security keys are going to be more important and critical over the next few years, because we're going to see that migration to an embedded system style of desktop and laptop, which increases the amount of security keys that are used, right? Because you've got, the keys that are required to integrate with other iOS devices, MFI style chips that integrate third-party applications and third-party hardware into Apple devices. All of those things require security architectures, and it doesn't make sense to create two separate models, one for desktops and laptops and one for iOS-based devices. It makes more sense to unify all of that. So an attack against a Windows-style laptop, desktop kind of thing will actually become more and more like an embedded systems attack over the next few years. So I would, in my perspective, stop looking at attacks as, is it Windows, is it Mac, is it Linux, and think more in terms of embedded architecture, which is really going to get you the best bugs long term. So this is the attack model, right? Especially for the demo that we did, is we find out what the physical address layer of the machine is. And then we figure out how machine layer code is representative in physical memory, because physical memory is separate from how the kernel sees the world, right? The kernel exists in virtual memory space. And so essentially, when you first boot a CPU, the CPU runs its first ROM code, right? The first thing that loads is essentially just something that sets up the secure world of machine layer, the highest privilege layer, right? So when you have an embedded device or a laptop or desktop or whatever, whether you call it machine mode or whether you call it the BIOS or whatever, this particular piece of code has to set up the physical memory environment in a way that the kernel understands how to use memory effectively. But that also gives that layer of privilege an opportunity to say, hey, kernel, you can only use this segment of physical memory, and I'm going to make it virtualized for you and tell you how to use it and slice it off for applications. So the machine layer actually sets up the initial page tables and hands it off to supervisor layer. The thing is that supervisor layer then can only interact with the page table directories because it's basically running in virtual mode, right? But here's the thing, the supervisor mode in the early version of the RISC-V architecture could alter all virtual memory. So the machine layer was not able to cordon off a slice of memory and say, you can't touch this virtual memory, supervisor, you're not allowed to do that. So what actually happened in the initial security model to gain execution layer privilege in the machine layer, all we had to do was get inside the kernel. That's it. And once you had access to the kernel, you could actually create a virtual memory map for the physical layer or the physical memory region that machine layer lived in, then make it writable in a page table. And then once you could made that section of memory writable by essentially creating a virtual memory map for it, you just overwrite the machine layer's code. And then you flush the TLB to make sure that the CPU's got the updated representation of what that code is, and then trigger a trap to machine layer. So basically what you're doing is you're manipulating that privilege model to say, hey, you may have told me that I can only play in this virtual space, but creating page tables allows me to create a virtual mapping for this physical area of memory. And you haven't given me any restrictions on which area of physical memory I can do that for. And so you just create a virtual mapping for the area at which the highest privilege layer code lives. And once you do that, you can overwrite it. Easy breezy, right? And then once you overwrite it, you just execute a branch to machine layer and force it to run your code. So that was actually a really excellent way of breaking out of kernel layer into machine layer. And it was an excellent attack against early RISC-V physical CPUs. So this wasn't a theoretical thing that happened. This was actually like put into practice. And we were able to do demonstrations with, the silicon at the time, which was really exciting. So this was kind of the methodology that I used to implement that attack. Not as relevant today, but if you're interested in the history and understanding how that worked, you can actually still implement it yourself by looking at the old versions of the synthetic CPU, running an emulator, and then doing the test yourself, which is a really great way of starting to get to know privilege layer attacks against a CPU, right? Because this isn't only about thinking about things from the shellcode perspective. It's thinking about it from a CPU architecture perspective to identify, is there an opportunity to not even use shellcode to increase my privilege layer from user land to kernel or kernel to CPU layer? And if we can do so abusing a CPU architecture level attack, there may be little to no, ROP, shellcode, buffer overflows. None of that is probably necessary. Like that's what was so beautiful and, elegant to me about this vulnerability is you were literally just telling the CPU to do what it was supposed to. But telling it to do what it was supposed to broke the security model of the CPU. It was a very beautiful attack. So the solution to that was quite simple, right? From an ISA perspective, we just say, okay, we can basically create a physical memory protection region and hand that off to the supervisor. So the kernel can only live within this particular region, and that's it. It can't do any virtual page table tricks outside of it. And that's that. So the PMP was proposed by the RISC-V team back in 2017. We now have a PMP. What's really cool about the PMP that you don't see in ARM as effectively is integrating PMP with not just microcontroller style CPUs, but also server level CPUs, which gives us a kind of flexibility that ARM just plain doesn't have, which is extremely exciting. And I'll get into that in a bit because the difference is substantial and the actual result is really important. So we have a fully open source ISA. And what I mean by that is you can take it and you can rebrand it, alter it a little bit, and publish your own version. So we actually have quite a few organizations that are building their own variants of RISC-V. We have absolutely no cost to play because it's open source, right? So you can literally just go to our GitHub and download the current version of the ISA and take that straight to silicon and go to like TSMC in Taipei and fab your own chips and have your own physical RISC-V CPUs in your hand in the matter of maybe a couple of months without paying the RISC-V group a thing. And the reason why that's really important is because the ARM model is a pay-to-play model. They recently open sourced the ARM Cortex M0 Plus variant of the architecture. They may have done so with the M3 as well. I don't quite remember. But those are extremely antiquated technologies, and that's only one version of the whole ARM ecosystem. I mean, we have, at the microcontroller level, we now have M55s, right? So we went from the M0 Plus or the M0 to the M0 Plus to the M3 to the M4 to the M4F to the M7, to the M23, 33, and now we have the M55. So we've really gone way past the initial implementation of even the ARM microcontroller cores. To now we have the M55 variant that integrates ARM trust zone security in a microcontroller class CPU. And of course, the M23, M30 all implemented a variant of trust zone as well, but they're reduced, right? The M55 is quite substantial because the M55 version of the microcontroller is going to be a 64-bit version of the microcontroller with trust zone enabled, or a subset of trust zone for microcontrollers in a microcontroller form factor. Like that's a huge leap forward. Having 64-bit microcontrollers, that's awesome. But let me say right? Because the cost of that is huge when you think about it from a royalty perspective. Now, if I want to build my own CPU, right, and introduce my own custom security technology, because, trust zone, as we know, as hackers, not so great, right? But if we look at that from a royalty perspective, I want to go out and build my own CPU and make it secure. If I'm doing that with ARM, I've got to pay them royalties for ARM and the ARM architecture in general, right? Because I'm not going to go use an M0 Plus or an M3. Why? They're so antiquated. I'm not going to do that. I want to use something modern, something with security that I can baseline from. That itself is a licensing fee. We've got royalty fees on every chip we sell. We've got to pay a percentage back to the ARM consortium for every single CPU that we build and sell, which can be anywhere from, like 0.5% if you're a huge volume seller to like, maybe 8%, as high as 8% per CPU if you're low volume or you're new or you're, not integrated to the ARM at a certain tier level. So the cost can be really high. And that's kind of the problem is ARM's architecture is such a pain in the ass because of their cost model that it's not easy to get new things into the ecosystem. Whereas with RISC-V, we can see all kinds of explosions because our architecture in its current definition, in its open source baseline definition, gives you all the tools you need to build a trust zone alike variant. And it could be 32-bit or 64-bit, and we have 128-bit ISA definitions, all open source without any royalty requirement. You can just download it, synthesize it, and chisel, and go straight to fab. That's a completely different model, right? And far more usable for somebody developing silicon. And we have FPGA and a completely open development ecosystem. And if you just want to download a RISC-V, specification variant in Chisel on our GitHub, and basically the Chisel app will synthesize VLSI that you can take straight to fab, right? Like that process is all open source. So I wasn't kidding when I said literally you can download a package off GitHub, synthesize VLSI, and take that straight to TSMC and get physical CPUs back in your hand. Like that's insane. It used to cost $2 million to $4 million on average just to get a proof of concept CPU that's like an ARM CPU. But because of shared wafers at TSMC, where you and other people pay all to have your chips fabbed on the same bus, you're basically sharing a wafer with a bunch of other companies to do proof of concepts of your silicon. But who cares, right? Because you only need a handful back to do testing. So you go out and you shell out, instead of $2 to $4 million, you maybe shell out $100,000, maybe $250,000. In some cases, you could get 10 chips back for 50K, right? Which is insane. And just go straight from an open source version of RISC-V to physical chips in your hand in only a few months or a couple $100,000 at most. That's insane. It would take millions of dollars and a year or a couple of years to get chips back in an alternative architecture. So iterating RISC-V is so much more cost effective today than it ever would have been, in my opinion, in the past. So that's pretty amazing. That's really exciting stuff. And we've got a lot of new technologies being implemented here. Everybody knows about tagging. So memory tagging at this point, this was a presentation from 2017 that's been updated, but I still wanted to talk about tagging, even though, 4 years later, everybody knows what memory tagging is. But memory tagging is still a new thing in ARM, Intel. We're seeing it more and more, and register shadows, shadow stacks, security related register shadows, like all of those things, memory tagging are exceptional. But that metadata is really hard to create, but it's not hard to create in an open source architecture. So we have low risks implementation that's doing memory tagging. That's Bunny. If you guys are hackers and you're familiar with Bunny's exceptional hardware hacking work, he's actually, I believe he's still a part of low risk, but he was there at the instantiation. They were trying to do memory tagging then. So I was really excited to see that they are continuing on. We've got Hex-V, which is doing some really exceptional memory-based security and shadow stacks and things of that nature. They're going to be very interesting in the future. So we've got a lot of really cool technology coming out, but there are limitations, right? Because whenever you take an open source implementation and introduce a new variant of that implementation, now you have to do a lot more testing because your solution requires more silicon. It requires more money to fab it. It requires more verification. Nobody else has done the proof on that verification. And so you need to ensure that there's going to be loss accounted for in your budgeting because, when you produce a CPU, there's going to be a percentage of failure for those CPUs, and you have to know what the estimate's going to be based on your circuitry. And all of those things have to get factored into the build. In fact, Thais, who's one of the Ring Zero team members, she actually tapped in on the last training that I gave this past fall. And she had some exceptional insights on that process that I didn't even know about, right? Because I have never gone through the fab process, and she actually has, I believe, multiple times. And one thing that she brought up that I found fascinating was just the idea of churn in building a CPU, right? Like when you spec it, you presume that it's like code where you just know, I have this specification, I'm going to take it to fab and I'm going to get exactly out of it what I expect to build. Now, if you've ever built your own PCB, you'll know that when you build a PCB, you're going to have a certain percentage of that circuit is just going to fail for build reasons that are just out of your control. Whether it's the layers of the PCB or something with the copper, or a particular component just didn't function correctly, or you have a high failure rate in a particular component that you picked. There are all kinds of reasons why PCBs can fail. So you estimate that based on your chosen bill of materials, you're going to have a certain percentage that is not going to succeed, and you account for that, right? You predict it and you do the best that you can. But what actually ends up happening is that same thing happens at the silicon layer in CPUs, which I don't know why that never occurred to me. Like I knew that there would be like a percentage of failure because that's just reality. But thinking about it almost as in terms of a mini PCB was really enlightening to think about how many different variations of failure can occur just by altering one little piece of chisel, right? So having an instruction perform things slightly differently or a little bit more optimization on the way that you handle your pipelines. All of that affects the output and can change your potential failure rate, which changes your budget, which changes your ability to execute. So when you have these new technologies, it really becomes a huge, overhaul to your process, and that affects the overall security. Because think about that from our perspective, right? Like, you can't protect a CPU to the degree that you want because these physical components will erode over time, right? The physical components of a CPU will change over the course of the lifetime of its particular implementation, of its particular, each unit has a lifespan. And I never really thought about that before, but it's really imperative in this world because the security models that we build from a CPU architecture perspective is not the same implemented CPU architecture that exists in that same CPU 10 years from now, right? And we need to know the physical degradation of a particular circuit. Is it predictive? To what degree? And at what point will it fail in the future? Therefore, we can know this security architecture is good for an estimated 5 years. And we have to guess 5 years because we know it's likely going to be secure for 10 years, but we see an estimated failure rate of 20% less than 10 years, which means now we have to sell it to our customers as a 5-year protected plan and then hope that it lasts 10 years, that kind of thing. And then think about that from the perspective of a car, right? Like, you're protecting a vehicle, but now you're protecting vehicles using a secure CPU that's been designed with a hopeful 10-year lifetime of being secure, but an estimated lifetime of, well, that silicon's probably going to be good for realistically 5 years. So you can only protect the secrets executed in that CPU for a 5-year span. After that, somebody could extract the keys. Next thing you know, somebody's driving your car off the road. Like, that's crazy, right? Like, I've never thought about CPU security like that before. And now that is just a part of the reality that we have to live in, that we have these systems that degrade over time. And attacking that security model is just fascinating, right? So one model for doing so is actually looking at the debug model, because the debug model, as we all know, is a huge part of protecting CPUs. So if you do any hardware hacking, one of the first things that you learn is the simple glitching bypass, right? Like, so if you're trying to access JTAGs so that you can just control the CPU and maybe extract some of the keys or firmware images that are stored in there, bypassing fuses using glitching is pretty straightforward. Like, you just alter the power level that goes to the circuit board and alter it in such a way that it believes that the fuse is still unblown, right, for accessing JTAG or downloading firmware or whatever. So you're essentially racing firmware to access that particular, for the CPU to access that particular fuse. You're changing the power level as it's accessing it to make it think it's something else. So you can bypass those protections using simple glitching attacks. You could actually just guess a debug password. Most debug passwords are very simple. A lot of them are 32-bit, so you can actually just iterate very quickly if you have a hardware test harness. Or you could simply just extract passwords from Flash, because unfortunately a lot of security models, and this is still true today as it was 5 or 10 years ago, there's no security in the actual PCB or the microcontroller used on the PCB. So you can actually just download the firmware and then find the password by reversing the firmware image. Those attacks are all completely usable, but in RISC-V, what we actually do is we extend the authentication model. So now we are altering the way that we think about debug protection, which is, can we use asymmetric secure keys, right? Can we define a basic authentication length? So can we use AES-128 or AES-256 or something that's non-guessable length? We're seeing more AES-128 in debug protections today, but those are only available within the past year or two, which is great. So now we have an open source implementation that allows us to poke at the authentication registers in such a way that we're protecting it, as well as testing whether or not they function correctly. So now that we've talked really deeply about RISC-V architecture and why the CPU architecture is so important, we can actually get into the architecture level from a user land perspective, right? So I know that's kind of like boiling the ocean to catch a single fish, but it's really important to understand, the background of the architecture from a deeper point of view and think about it from the privilege layer model, because it makes even the application layer attacks so simple. Like, you stop thinking about things from an app perspective, and app perspective hacks can get so complex because we're thinking about the shellcode, we're thinking about ROP, we're thinking about, what libraries are involved, what system calls can I abuse? There are so many things that we think about because application layer security is so variant, right? There's a diverse world of code in the application layer because it's opened up to all kinds of unique applications. But the rest of the architecture is really not, right? So it seems like sometimes it's more daunting to think about it from a CPU architecture perspective, but it's so important to dive into that because once you do it once, almost every CPU is set up in a similar fashion with some subtleties, right? Because RISC-V has its very strong, unique subtleties, but it's really not much different from ARM. It's not much different from MIPS or Spark or even Intel or whatever. And once you have that down, the application layer attacks become very streamlined. So here, like Thumb, we have a 16-bit opcode set. So we have no context switch based 16-bit opcodes. So the embedded systems variant, like ARM's Cortex-M is, we have a very clear analog for that in RISC-V, but it's really just the same ISA, whereas in the ARM world, the Cortex-M line is vastly different from Cortex-A and Cortex-R. Cortex-A, or the application type CPU for servers and laptops and desktops, is a completely different beast than the Cortex-M. And Cortex-R, or the real-time variant of the ARM architecture, is very similar to Cortex-A, right? Those two things are almost the same beast. One's just more optimized for real-time processing, but the overall architecture is very similar. Whereas if you look at that as a differential between the Cortex-M and the A and R, the M is a completely different beast. The entire architecture spec is completely different. It introduces different concepts. BMP is available in M, but not in A and R, where there are A and R variants that aren't quite the same. Whereas in RISC-V, in my opinion, RISC-V was done correctly in that they defined one ISA and then allow you to pick and place the variations of the ISA that are right for your implementation. So the embedded system is just a subset of the actual core ISA spec. It's not a completely different spec for the embedded environment. And that's a really important variation because, again, because we're open source, because we don't have any royalty, because we don't have any fees for implementation, no kickbacks, right? We can build, one organization, a new startup can build a server class CPU from almost the same spec as an embedded CPU by just adding a couple different things, and that's it. So it becomes extremely streamlined. So that's pretty much the overall architecture itself. But there are a couple of things that I want to talk about separate from that, right? So recently, we had some exceptional work done, and I'll just switch over to video for this. We don't need to see any more of that junk. Cool. So Okay, I'm not broadcasting anymore, but there we go. All right, so there are a couple of things that we need to touch on aside from the generic application mindset, right? Because we've got standard CPUs in RISC-V, just like any ARM. So you have essentially 32 generic registers, and that register set, they're all based on the ISA length. So if you have a 32-bit architecture, they're 32 bits wide, 64-bit architecture, 64 bits wide, 128, et cetera. All very standard. So the thing is that if you're attacking it from a shellcode perspective, it's almost the same as ARM. If you're thinking about that from an application layer, your attack model is almost the same. The only difference is that like the R0 register is null only, both read and write. And aside from that, it's basically the exact same thing. So what's really cool about this is if you're developing embedded systems or you're actually building an attack for an embedded system or an application, and that same application is available on ARM and RISC-V, the only thing that you have to do is just build your ROP chain for the specific compiler, and that's it. You can actually just use GCC to output for RISC-V or ARM or whatever architecture you want. And that's all the work that you have to do. There's no other special ingredient in order to implement an architecture or an application layer attack. And the rest is really just up to you to identify the ROP-based methodology that you want. And that really is just understanding how to reverse assembly for RISC-V. But if you get used to it, it's a risk, right? So anybody here that's worked with ARM, if you've seen the ARM instruction set, you're used to, load integer, load address, load and link, or jump and link, jump register, all those kinds of things. They all have the exact same analog in RISC-V. Now, it's not that RISC-V is copying the same things from ARM. It's that it's a RISC-based processor. And if you're familiar with any RISC, you're familiar with all of them, right? Because PA RISC, HP's old RISC variant, was really the only deviant, historically. And what I mean by that is in the PA RISC architecture, the stack grew up from the bottom. It didn't grow down from the top, right? And it had quadrants for memory instead of actual memory, physical zones, if you will, right? But that's the most unique variant of RISC there was. And it was mostly because PA RISC grew from the bottom up. And that's it. But the registers, the same. The names of the instructions, the same. Sometimes, a lot of the times, the encodings for instructions, very similar. Spark was the same way. Spark, MIPS, PA RISC, ARM, all of those things ended up having a very similar set of instructions, set of encodings, set of registers. The conventions were even similar because people were trying to encourage people from other architectures to come over to theirs. So it ends up all using the exact same methodologies over time. They kind of collapse into one unified architecture without intending to, right? And that was actually a really fascinating thing, but that kind of gives you an idea that if you had a really diverse 0-day back 20, 15 years ago, and you could attack a MIPS, a Spark, a ARM, or whatever, you could very easily tune your shellcode based on the architecture that you were attacking because there was so little work to do for RISCs. And any Unix variant at the time was going to be using a RISC-based processor. It wasn't until Sun Microsystems Solaris 8 that they even supported an Intel-based processor, right? Everything else was PowerPC and Spark. They didn't, ARM didn't even show up until later in the game. So that kind of gives you an understanding of like, once you understand one RISC architecture, they're all the same. And there's really nothing to talk about. Like I can give you instructions on how to build shellcode. And if my hotspot was working today, we actually would dive in a little bit. But there's really not much to do, right? Like when we talk in February about RISC-V hacking, we'll do some really streamlined shellcode development. But the shellcode development is going to demonstrate how you can produce shellcode for RISC-V with almost no effort, right? Because all it requires is a couple tune scripts and a little bit of code written in C on your part, and then you can literally just compile it all and run it. And that's kind of the thing about advanced exploit development, if you're interested in that, and not just architectural hacks, because once you learn that, the way that you set up your environment in your exploit defines how your payload will function. And if you set it up in a really simple, streamlined fashion, in that you're almost setting up your own kernel inside of the application you're attacking, then you can literally just compile your own code as if it were an application and load it into your exploit runtime. And that's it. You don't have to do anything magic with ROP. You don't have to do anything magic with all different kinds of things. You almost use the exact same ROP payload every time you develop an exploit after that. Like, there's very little you have to tune except tuning it to the available code in the particular application you're targeting. And that's it. And that can almost all be automated. So I'll demonstrate how you can do that in our training, which I think some of our friends may be a little bit mad at me about that, because, you know, some of our friends do a really excellent job of demonstrating how to develop zero-day and how to develop exploits and tune them to a particular environment, tune them to a particular application. And those are all good, important things. However, it's not necessary, right? Because we have advanced in exploit technology to the point where, you know, we kind of have a canned environment. And once you understand all of the fundamentals, and once you have those primitives down in setting up your exploit environment, it really becomes kind of like your own Python interpreter. And then you just load your Python right into it. And there you go. Your exploit payload can be custom every single time. But if you understand how to formulate those primitives, you create the operating system for your exploit code, right? And that's all you need to do. So the fundamentals of RISC-V are no different than any other architecture. You've got your basic generic registers, but in an embedded environment, you can just choose to reduce the 32 registers to 16, and that's it. You have a couple other gotchas, as in, like, you know, we're going to use 16-bit encodings for instructions instead of 32-bit encodings, but that's the compressed variation of the RISC-V ISA, right? It's meant to do that. So that's a really easy thing. You just add that capability onto your CPU definition, and now your silicon that's synthesized through VLSI will automatically be able to use those compressed instruction sets. So there's really nothing that you have to do. You basically just select the variants that you want, add them into your CPU, and go to fab. That's it. From an attack perspective, when you're attacking the application, if the application is capable of 16-bit encodings, or it's only using 16-bit encodings, you just change the output of your compiler, and there's one compiler switch that says just produce compressed code. That's all you have to do. It's very simple. So the beauty of the architecture is in the definition of the architecture. And to get back to the privilege layer thing, this is what I really wanted to talk about in regards to ARM's trust zone versus RISC-V. And this is the imperative nature of understanding RISC-V, why this is going to be groundbreaking, right? And why the security model attacks are really important here. Because in ARM, a lot of people don't actually know this, but trust zone is really a hypervisor. And what I mean by that is, if you have trust zone, even if your CPU isn't capable of being an actual hypervisor capable CPU, it is if it has trust zone, because what's happening is the highest layer of privilege is switching context back and forth from secure world to normal world to secure world. And the way that it sets it up is it actually creates a layer of virtualization that it can context switch back and forth. Now think about that from an attack model perspective. You have to either get underneath the virtualization layer, or you have to figure out how to compromise secure world. Surprisingly, that's very easy to do in ARM, because number one, the ARM privilege layer is usually set up incorrectly. And when you have trust zone enabled system, the firmware is usually written very poorly. So it's very easy to attack. But the problem is that when you have a trust zone implementation, a lot of times the trust zone vendor will just give you a blob of code and say, this is what's going to go in your trust zone. And you don't even get to know what it is. You just have to put it in there. It's like the back in the days with Broadcom, where they would just ship you a chip, and then you'd have to use their firmware. And you're like, what is this? And they would say, we're not going to tell you, because it's all their IP. This is very similar in trust zone. And we've found over the years, there have been a lot of really great talks at Black Hat, at Hack in the Box, at wherever, attacks against trust zone implementations, because we see that. It's a proprietary implementation. It's not fully formed. It's not fully fleshed. And when it goes to production, there are significant and standard buffer overflows that allow you to go into secure world. In RISC-V, it's not that way, because we have an open architecture, and it doesn't require a hypervisor in order to implement multiple secure worlds. In fact, you can have as many secure worlds as you want in RISC-V. It's not only limited to secure world, non-secure world like we have in ARM. In RISC-V, it's basically at the machine layer, the highest layer of privilege, we define physical memory regions. And each physical memory region can then be attributed to a particular supervisor world. And that supervisor world can either be secure world or not. That depends on your implementation of not only your CPU, but also just the boot code. If you flash firmware into a RISC-V CPU at the machine layer can literally configure 16 different secure worlds and run them all concurrently based on how many cores are available in that processor, right? And that's really exciting because there's no virtualization. So if somebody compromises one secure world, they cannot then compromise all the secure worlds at once. That's not possible. They only compromise that one supervisor, and that's it. Question, I guess you still have slides to show, but you're not sharing the slides. Oh, actually, no. The slides have run out, unfortunately. So I'm just talking now. But we've only got a couple of minutes left. But thank you for pointing that out. But yeah, because of the hotspot issue we have here, I can't even upload my slide that I made for this, which is really unfortunate. But that's the problem with being in the middle of mid-Michigan. Sometimes your hotspot works, sometimes it doesn't. And when it doesn't, you can't drive 2 hours to the place where it would. So apologies for that. But the one last point that I really want to showcase here, and not just on that trust zone-like nature, right? And you can visualize it really easily without me even having slides, because you just think about it as if you're standing in a house and each room in the house either has a normal door or it has a secure door where it requires a key to get into it, right? In an ARM environment, you've literally got the front door and everything on the inside is open. You can go into any room you want and do whatever you want. In a trust zone architecture, you can go in the house, but there's one room in the house that you can't get into unless you understand the key, right? In RISC-V, every single door to every single room in the house can have its own unique key. And that's really cool for two reasons. Number one, because in RISC-V, we don't have any licensing associated with that stuff, right? So once you have that key set up, and your houses and your rooms created, like that's all you have to do. Once you do that, like you've got as many secure worlds as you want and you have them for no cost. Whereas in an ARM architecture world, you have as many secure worlds or as many trust zone worlds that are available to that implementation of the processor. And that's all you get. But in RISC-V, we can do it based on the firmware that's executed in machine mode. So it's not implementation dependent. It's literally basically, what firmware do you want to flash as your secure boot, and then just build whatever you want from there. So the security model is really exciting because we can do things and build architectures at no cost that have far better security ramifications than anything we've seen before. And tagging that is really interesting, right? Because even if you compromise one supervisor world, whether it's a secure world or not, it can't actually move laterally, and it can't go into machine layer without an additional 0-day. So that's really exciting. And the other thing that I want to talk about briefly, because we've only got a couple minutes left, is CPU-based attacks are getting more robust. So the NVIDIA security team this past DEF CON released a very clever attack against the RISC-V architecture. So another bug that was found in our ISA was the NVIDIA attack against our trap vector setup. So if you're familiar with configuring a CPU, the first thing that you have to do at CPU boot up is alter the trap vector. Now, for those that don't know, a trap is essentially an interrupt that occurs at the CPU layer to handle context switching from a normal application to an event. And an event can be like, we had a divide by 0 error, and that needs to be accounted for. It could also be, we got an interrupt on an external bus, like a high level on a pin that's defined as a GPIO, and that creates a trigger, an external trigger. Or you could say like this serial bus has a high line, which is indicating that serial data is coming in and the driver needs to, download data off the serial bus. All of those are traps. And the trap vector defines the address in memory where that code starts to handle those traps or those external events. But those external events can be triggered also by software, as in context switch to a higher layer of privilege, as in the supervisor mode, the kernel can request resources from the machine layer by executing a trap. The user LAN can make a request from the kernel by using a trap. So that register that's MTVec or machine trap handler vector, that register needs to be set in order to process incoming events, right? So the first thing that you generally do, and this is true of all architectures, whether you're Intel, RISC, ARM, whatever, they all require at least a trap vector that branches to a set of instructions that handles a particular event. In RISC-V, MTVec, that register is the register that handles that, right? So the first thing that you do on any of these architectures, generally when you cold boot, is write that register that handles all those events, because until you do that, you can't handle any events, right? So there's a race between when the processor turns on and when that register is written. And in the current implementation of the ISA, the way that it was addressed is, well, you just write this register whenever you please, and that's when you start handling traps. But if a trap occurs before that, it's unhandled, and it's, we don't know what's going to happen. Depending on the implementation, it could just reboot, it could, ignore it, it could do all kinds of things. So what NVIDIA figured out is if you have a secure implementation of a RISC-V CPU, as soon as it boots, there's a window of time between the booting of that CPU and the setting of that register. And the result of that is implementations will define that register as unset or unknown until it's actually set. And because of that, you can glitch it. So here was the interesting thing. NVIDIA set up a testing harness that allowed them to glitch that register and put an arbitrary address in that register because of the glitching. So again, when you're glitching, you're changing the power level of the CPU as the CPU is reading data from memory or from a register or from some kind of place where it needs to use electricity to define what is stored in that object, essentially. And so when you're glitching it, you're basically trying to trick the CPU into reading a different value than what's actually there, right? So when it's actually defined, when it's written, that's going to be much harder to glitch. But when it's undefined, it's easier to glitch because there's no definition for it yet, right? The CPU hasn't set what those bits are supposed to be, which changes the cache coherency of that particular register. There are a lot of subtleties in the CPU as to whether or not it's set. But if it's not set, it's easier to glitch, and it's easier to glitch at the very start of cold boot than later on, because as soon as the processor boots and you induce a trap by, say, setting a GPIO high, GPIO, the first thing that processor is going to do as soon as it cold boots is try to access the trap register. So it's not like, there are 1,000 different instructions that are all happening concurrently and you don't know the order of it and you're trying to create a glitch circumstance later on down the line. Like, that's almost impossible. Like, it's really hard to do. And you need special circumstances and tools in order to do that successfully. And it's not easy at all. But if it's the first thing that happens on boot, it becomes very, very easy to predict and very easy to glitch, or easier. So what the NVIDIA team did is essentially, as soon as the processor comes online, they induce a trap using an external GPIO by raising it up. That causes the first thing the CPU does to access that trap handler in the MTVEC register. And because it's reading an undefined register, you would normally just crash or whatever the implementation is going to do. But if the glitch succeeds and it reads a register address out of there, it will try to branch that address. So before the secure CPU can even be set up, you can glitch that register, induce a trap, and trick that secure CPU into jumping to your code instead of jumping to secure boot code, which means that you gain immediate control over the executed code inside the secure CPU before it becomes secure. And that's huge, because that means that if the code is running in ROM, like one-time programmable ROM inside of the CPU's internal memory, you would never be able to overwrite it. And you would never be able to alter that even with JTAG access, because it's just part of ROM. Like, you're not going to change that, right? But if you can glitch that register before it's set by the ROM, you can point the address of that register to external memory, in this case, memory accessed over SPI, and then jump into code that you can write in SPI with no problem, right? And so that's what the NVIDIA team did, which was really clever. So they demonstrated that in DEF CON this past summer. And the reason why I want to bring that up is for one primary reason. It's because when we think about attacking applications and attacking CPUs, we often think about it from the application perspective, right? But there are all these subtleties that we've been talking about behind closed doors for over a decade now about the subtleties of CPU attacks. And I certainly have been one of the least skilled people in that space. I've been lucky to poke at that space a bit, but there are people that are exceptional at it. Ralph Philip Weinman being one of them. Guy's been hacking CPU errata, especially in ARM, for like 12 years. He's just a genius at it, right? And he's been using that to do car hacking stuff lately and all kinds of things. I would consider those guys to be an expert at it. Thais, exceptional at that kind of stuff, right? The Intel team has a great team that focuses on CPU level attacks. I believe, God, there's somebody else whose name is on the tip of my tongue. I guess it doesn't matter. But there are a bunch of people that are really amazing at it, that are only really starting to get light shined on them, because we're realizing that application-based attacks are good, right? Like we still need good 0-day at the application layer level, but secure keys are becoming so much more critical because everything's migrating to this embedded systems model, even desktops and laptops, that it's becoming more and more important to look at the CPU-based attack style. That perspective is becoming more imperative than ever before. And there's so much to do in that space because, again, when we think about CPU security, we're now thinking about it from the perspective of this CPU architecture is only viable in production in the field for 5 years before it starts to degrade. And at what point does it start to degrade to the point where that security model cannot be protected 100% of the time in the field because this circuit is going to degrade and sometimes it's going to make a decision that it shouldn't make? That's weird, right? That's a weird world to live in. That's like software, C language software that's been written for 30 years that suddenly decides to make a different decision than normal for no reason, right? That would never happen. That's absurd, right? But in the CPU world, because of the way that things degrade over time, and especially at the nanometer level that we're starting to work in, where we have sub 170 nanometer silicon, now we're starting to get in a really weird territory that things don't live as long as we thought they would. And the side effects of the degrading security and the degrading circuit can be huge. And if we can't prove that a CPU is viable for 20 years with a stable security model, how are we going to put that in a car, right? How are we going to put that on a plane? Those are really important things to think about and scary things to think about. But how is that going to shape the world moving forward, right? So this really isn't just a training about hacking RISC-V, which it is, right? But I think after hearing me talk about the RISC-V architecture and how it relates to ARM and how it relates to Intel and all these other architectures, it's less about RISC-V, and you'll get a full picture of how to hack RISC-V itself. Application layer level hacking, debug style hacking, glitch style hacking, privilege layer architecture style hacking, but also the big picture on this is how we're thinking about attacking in offense moving forward, because we've shifted the model. This is no longer an ecosystem where we're focusing on, you know, the application style bugs of the past. Now we're thinking about it in terms of how is the future of computing going to be altered by the way that embedded systems are designed, implemented, and sustained over time. And that's a much weirder world to live in. So if you're interested in any of that, CPU style attacks, RISC-V itself, application hacking in RISC-V, and you want to see that next world of information security and offense, please come join us in February because it's going to be very fun. I'll put it that way.